Okay, we're gonna add, what this boils down to today, we're gonna add a little element to, our, our tables that we've been talking about. So if I should probably give you like the objective. Here's the objective. So we're going to be looking at limits at infinity. Okay, is kind of what this should be called in calculus. Sounds a little strange, but this is the really, really minor league. I mean, this is very, very, very simple stuff. Yes. Simple stuff. Comparatively, compared to the other stuff you're doing, this is really a little sort of a break in the action. So, what's that?
Is that Q?
That's a P and a Q. Yeah. So this is
first
of all, yeah, it's
I had a G
P and a Q. So, definition of a rational function. A rational function is just a function that can be written as a ratio of polynomials.
Which one, the P or the Q?
So both of them are. So if you have a ratio of polynomials, that's a rational function. I think we've talked about that before, but just a quick reminder. So let's take a look at a limit like this. We're going to take the limit of this rational function. Now, it's going to look a little strange as x approaches infinity. What does that mean?
Oh dear.
What's that?
As x gets really big to the right.
Yeah, as x gets really big to the right, exactly. As the number gets big and positive, okay, without limit. So we're looking at the behavior. Now, a lot of times in math, we'd say we're looking at the behavior of the tails of the function, so way out to the sides. We want to know what's going on. We're looking at the right tail of the function. We want to see what's happening out there. Okay, so if we try to, now, you got to be a little bit careful when you're dealing with infinity because, we've done a little bit of this. Infinity is not a number, right? And so technically, you can't evaluate a function at infinity. That's because you can evaluate a function at a number, something you can just substitute directly for the number. But you can kind of do that with infinity too a little bit. You know that a lot of times, and you have to be a little careful with it, but the meaning isn't exact, but the concept is well understood. So if I tried to plug infinity in, meaning just an arbitrarily large number, we get what on the top and what on the bottom? Infinity, right? And so we end up with, if we evaluate directly, which is a little cheesy to do, it's not, you got to take it with a grain of salt, but if you attempt to do that, you get something like that, which is an indeterminate form.
What?
Okay, just like, remember when we had 0 over 0, that was an indeterminate form, right? We took limits and we said, they're going way back at the beginning of the year, we took limits, remember this stuff, and we said there's 3 kinds of answers we could get. We could get numbers, right, top and bottom, which is an answer, right? We could get a number divided by 0, which at the time we said was no limit. Since then, we've gotten a little more precise with that. And then the third type was, both of those we were done though, right? I mean, that was done with the limit. Third type was 0 over 0, which always meant more work. Yeah, because that too was an indeterminate. Whoops, stop writing. That too is an indeterminate form. Okay, so this thing is scanning or something. What's going on? Okay, so this too, you might guess this too requires a little more work. We don't know what it is. We have to find out what is that. It could be anything. So what do we do? Suggestions.
Just put it as one.
Actually, there's something called L'Hopital's rule, which we haven't learned yet, but that is really.
Derivative of infinity?
I'm not going to talk about that now, but no, the derivative of the function. When you have an indeterminate form, and I'll show this to you later, kind of towards the end of the year. But there is a trick where you can just differentiate the top and the bottom until it's no longer indeterminate. That you really, I mean, that actually is
Smart.
something.
That's cool.
Smart.
It's pretty handy, actually.
So we gotta do some more work, you know, we got to be creative about this, and this is a different look than we've seen before. Now, the good news is, we're only gonna have to do this once, and then we're gonna see a pattern here, and we'll never really have to do this process again. But we gotta go through the work once. So how are we gonna get rid of this indeterminacy? Now, remember, a lot of times in the past, our goal was we wanted to try to factor stuff out and cancel common factors.
Mhm.
Okay, right? So,
Should we do that here?
yeah, well, I mean, what do you think? Is there a way we could do that?
Yeah.
Okay, what if we factored out the greatest power of x? Good idea, right? So if we're gonna factor out, let's say, an x cubed from both the top and the bottom, right? Good idea. So that's gonna give us, if we do that, on the top, we're gonna get x cubed times what left over?
Whoa. Yeah.
Okay, that's it, right? Because factoring just means dividing, right? That's all it is. Factoring is a process of division. When I factor out an x cubed, aren't I just dividing each term by x cubed to see what's left over? So what's your rule for dividing exponents? If I divide like bases, you subtract the exponents, right? So really, we just end up here with a 2x to the minus 1. I'm going to go ahead and write that as 2 over x. Does that make sense?
Wouldn't did we just put an x cubed out in front?
Well, we're not, because remember, when we factor something out, we're not changing the value, we're just changing the look, right? We're undistributing.
okay.
Factoring, another way of thinking about factoring out a greatest common factor is really just think of it as undistributing. So if we undistribute an x cubed, you can kind of ask yourself, x cubed times what would be 2x squared? Well, I'd have to cancel one of those x's, right? I've got an x squared, and so I must have an x on the bottom.
Yeah.
Okay, does that make sense? It's a little odd, but does that make sense?
Mhm.
Okay, what would we get here?
Over x squared?
1 over x squared. Okay, however you want to think about that. I could think about it as x to the 1 minus 3, right? X to the minus 2, which is just 1 over x squared. And then finally, 3 over x cubed, right? So that's the top. What about the bottom? First term?
1.
1.
Yes,
Plus
we can do-
4 over
X squared.
x squared minus 11 over x cubed. Okay, and so algebraically now, we can go ahead and cancel the x cubes. Right? Okay, yes.
Can you re-explain how you got the first term in 2 over x?
Sure. So all we're doing, to find out what goes there, really all we have to do, if we're factoring out an x cubed, we're just gonna divide the original term by x cubed, right? So that equals 2, and then x squared over x cubed, well, I can cancel 2 of those, leave me with an x on the bottom. Whoops, sorry, so 2 over x. Oops, there we go. That's what goes there. Okay, and the same process for all the terms.
Yeah.
Okay, so now though, now we can actually evaluate the limit, but this is a little strange. What's that gonna be? If I try to take this limit as x approaches infinity, what is, for example, going to be the value of 2 over x in that limit? Okay, now what's that gonna look like? Right, if we try to evaluate directly,
Very small.
we get 2 over infinity, what's that start to look like?
0.
Yeah, that starts to look a lot like 0, doesn't it? Think about the behavior of a fraction. Fractions can get small in 2 ways. We could make the numerator small, right? And that would make, and hold the denominator constant. That would make the fraction small. For example, compare 7/8 to 1/8, right? The other way would be to hold the numerator constant and make the denominator big, right? Compare 1/10 to 1/100th, for example, right? Get the idea? Okay, and that's actually, in your book, there's a fancy highfalutin theorem, I don't know what they call it here, limits at infinity, and it just looks like this. It's nothing, it addresses that very idea. Just says, essentially, if r is greater than 0, r is positive, rational, and it doesn't have to be rational, it could be any real number, and c is any real number, C is an element of the reals, then this is what we know. We know that the limit of C over x to the r as x approaches infinity, constant over any power of x as x approaches infinity is what? What's the limit going to be?
0.
0, yeah. Because the bottom is going to get big without limit, and the top is going to stay the same. And so the fraction is going to get vanishingly small. Yep.
What are those, ROC?
This stuff up here, all this weird cryptic stuff, this says r is greater than 0. That's supposed to be a greater than.
Okay.
And this says C is an element of, this kind of math symbology. C is an element of, so that's the symbol for element of.
Okay,
And then the script R is what represents the set of real numbers.
okay.
Okay. You don't have to know that, but I probably should start to kind of show you guys some of that stuff, you know.
C is a trident?
Is it trident? Yeah. Okay, so that applies.
He with the tail.
That applies here, doesn't it? And we end up with a lot of stuff going to 0. In the limit, as x goes to infinity, look at all the terms that are going to go to 0 then. Every term with an x of any power on the bottom is going to go to 0, right? So that goes to 0, 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 but that stays, right? And so we end up in our limit 0 over 1, which is 0. Okay, so hold that thought. We're going to look for a pattern here, okay? There's Exhibit A. Let's do another one similar to that. We'll come back to it. We'll see if we can see what the pattern is here.
I like that.
So let's try the limit of any predictions? Any predictions what the answer's gonna be?
No.
1, Karen?
10. No.
Okay. Well, let's see. So we're gonna use the same technique, right? If we want to try to, the more work in this case amounts to factoring out the biggest power of x, which in this case would be x squared. Okay.
Yes. Tis. That's right, brother.
2 of them high.
So what's left over in the top if I factor out an x squared?
Where did you get that?
Okay.
I already taken it out.
Bottom? Okay, so the x squareds cancel algebraically, and in the limit x goes to infinity.
Cancel out all the, I can 0.
Yeah, everything with a constant on the top and an x on the bottom.
You're gonna have 2 over 5.
Yeah. And so we end up with 2 over 5 for our answer.
Let's go.
Nice job.
Oh, God.
Right.
Yep.
So he's like, oh no.
Okay, so that's the limit. Okay.
I don't like it.
Yeah, it is. It is gonna be easy, yeah. Okay, and then so there's Exhibit B. Now Exhibit C.
Sounds like a test on this is worth like.
Cool. Yeah,
It'll be a
like-
part of the test, I'll give you that.
Part of the test.
Thanks, kid.
Not just a test by itself.
No, not quite. Okay, now what?
I see what's going
Thank
on
you.
here.
Oh, cube
No,
or
we gotta do something over zero.
So take out an x squared, right?
Yeah.
It's like 4, okay. So,
It's
The stuff we did earlier was
Taylor, are you not seeing it?
It's positive zero.
Oh.
God, okay, don't like.
okay, agreed? So algebraically, those go away. In our limit, all this stuff goes away, right?
11.
Now, we gotta be a little bit careful with this one though, right? On the bottom, this is going to 0, right? But as x approaches positive infinity, I get 12 over positive infinity, which is a positive over a positive, right? And so it's 0 positive, isn't it?
Yeah.
Right, okay, so
It's that little.
it's a 0 plus on the bottom, right? So we end up with, in our limit, we get 3 over 0 plus. Now, originally, at the very beginning, we would have just said no limit, but we got a little better than that, right? When we started talking about one-sided limits, what did we agree that was? 0 on the bottom means what? Now, it's not actually 0, is it? It's just a very small number. 3, a big number, a relatively big number on the top divided by a very small number on the bottom means the fraction gets very big. So we know that the fact that we've got a 0 on the bottom means that it's infinity, but we just need to know what flavor, positive or negative. Positive, yeah. Okay, so it's positive. Now that's important because we want to know, wouldn't you agree that if we're trying to, really what this is going to contribute to is our ability to describe the broad behavior of the function. We want to essentially sketch a curve. So if we're going to sketch the curve, it's very different to say that it's going clear up there or clear down there, right? Yeah.
So if the 3 was like a negative, it'd be a negative.
Yes, yep, mhm, exactly, yeah,
And if it was like negative 3 and 0 negative.
yep, exactly. Okay, so now, see if you can describe this, sir.
Why is it 0 plus?
Why is it 0 plus? Because
See, I got you.
12, because as x approaches positive infinity, we're going to end up with positive 12 over positive large number, say positive infinity. The sign rules say positive over positive is,
Oh.
right, positive. We know it's going to be small because the bottom of the fraction is getting huge, but we need to know, is it a small positive or small negative number? Yes, sir.
Okay, so then why isn't that 1 over x? Also, 1 over x.
Okay, good question, yeah. The reason we don't really care about the 1 over x is because on the top, now think about on the top what we've got. We've got 3 plus, nothing. And so whether that's positive or negative, what's the limit on the top going to be regardless? 3, right? See what I'm saying? The only reason that we have to be careful about this one is because 0 happens to be the special number that's right between all the positives and the negatives. So we got to really know. You see that make sense?
So just
And by the same token, why don't we care about this one while we're talking about it?
it's square.
Because it's squared, and so this is going to sound a little strange, but a lot of this stuff sounds a little strange. But if I've got an x squared on the bottom, that's an infinity squared. Which of these two terms is guaranteed to be bigger? Even though they're both approaching 0, this one is approaching 0 much, much faster, right? I mean, excuse me, much, much slower. This one's approaching much, much faster, sorry, right? In fact, it's approaching how much faster? Infinitely faster, right? Because it's, I mean, isn't that weird? I mean, but it's, yeah.
Oh, God.
So all we really care about then are the leading terms. Now, another way to do this, I hate to, beat a dead horse here, but this thing is, there's another way we could look at this that might even be a little easier to see. It's gonna accomplish the same thing. What if we just factored out an x instead of an x squared?
Yeah, let's do it.
Let's see, what's that gonna do? If I take this thing and instead I factor out an x, yeah, I'm gonna get 3x plus 1 minus 7 on the top. On the bottom, I'd get x times positive 12 plus 4 over x, right?
Isn't it 7 over x? Yeah.
Oh, 7 over x
Plus.
squared even. No, just
No,
just
it's
x. There we go,
yeah.
okay.
There we go.
Okay, so
Yeah, I agree.
x's cancel.
Yeah.
In my limit, look what happens here. This goes to 0, that goes to 0. So as x approaches, it's a little easier to see almost, isn't it, for this example. As x approaches infinity, what's this going to become?
Super big.
Yeah, positive infinity, right? I get positive 3 times positive infinity. So we get positive infinity on the top. On the bottom, I get positive 12. Well, what's that going to be? Positive infinity on the top divided by positive 12 on the bottom is, that's going to be,
Positive, super big.
yeah, it's still going to be positive infinity, isn't it? Does that make sense?
Either way is what's infinity?
Either way, it's positive infinity. Whichever way you want to do that. But here's the good news: you don't have to do it anymore because we're going to establish a pattern here that's going to
yes.
prevent. We're going to know what the pattern is now, based on. Well, you're going to tell me.
Oh, no.
So compare these three situations. Exhibit A, we had a limit of a rational function as x approached infinity, and we got 0, right?
Yeah.
And by the way, I could even do this. I could even say, for this one, I could have made that plus or minus infinity. Didn't matter. Didn't matter a bit in this case, did it? Doesn't matter if the bottom, really it makes no difference. 0 divided by a number is 0. This is approaching 0, right? Irrelevant of which direction we're going. Okay, try to see a pattern. So that one gave us 0. This one, plus or minus again, doesn't make any difference. This could have been a plus or minus infinity. Either way, we got back a constant value at 2/5. Okay, look at that one. See if you can see the pattern.
It's an 8.
And this is the one that blew up. So what's the pattern for a rational function? I'll just give you see if you can, without doing any work, you can tell me what this answer is going to be.
Oh, it's 0. Yeah.
What's it going to be?
0.
0. How'd you get it?
Because on the bottom has the biggest x.
There you go. Okay.
If they have the same, if the exponent it's the highest for it would be 3 on either side or something, and that would be the highest, then it would be the constant one, right?
There you go. Okay. So the rule is, if we have a rational function and the order of the polynomial on the bottom is bigger, then the limit's going to be 0. The limit at infinity, plus or minus infinity, is going to be 0, isn't it? That's pretty easy to rationalize. That's no pun intended. We can see that because if you think about the strength of the polynomial, that's telling you, infinity to what power, right? Well, the top is an x squared, the bottom is an x cubed. When I evaluate that at an infinite number, positive or negative, the bottom one is x more powerful than the top, isn't it? Right? So it's infinitely more powerful, because x is approaching infinity, than the top. And so the bottom is going to get big infinitely faster than the top. They both get big. They both go to infinity, but the bottom one goes there infinitely fast compared to the top one, right? And so the answer is, well, the bottom wins. Bottom gets a lot bigger than the top. Big on the bottom for a fraction means 0, right?
Yeah.
Does that make sense? So that's easy to, to kind of reconcile, I think, with the talk we've been having. So that one's always going to be 0. Okay, and then if we have something like limit of 7x² plus 5 over 3x squared plus x minus 4.
7/3.
It's more.
Right. Now, they're going to infinity at almost the same rate, right? The top one, this one's going 7 times x squared, this one's going 3 times x squared. Do we even need to worry about this other stuff? No.
They go to 0.
No, the leading terms are gonna dwarf everything, aren't they, right? This is all we care about, is that stuff. All this other stuff is just minor league.
Just for fun.
It's just gonna be small, right?
Add a little.
And so, if you look at the ratio of the leading terms, the x squareds cancel, and I just get a 7/3, right? So the top's going a little bit faster, but not a ton.
Nice. We were on this.
So we might say it this way. A limit at infinity, positive or negative infinity, where the orders of the polynomials are equal, always ends up being just a ratio of the leading coefficients. Okay? So easy, right? Those are done. The one that's maybe a little bit tougher was our third case, and that's the one where you gotta pay attention to the sign. That's the only thing about it that you gotta be careful of. You gotta pay attention to the sign of the infinity, because that's, that's a lot different than that, right? If you look at the shape of the curve. So let's practice one of those. So what about?
Happy birthday to you. Happy birthday to you. Happy birthday, dear Whitley. Happy birthday to you.
Kevin, you gotta
step
step
up
up
right
right
there.
there. That was like a 1, 2.
Got him. Nice job. Step up right
Okay, what about this one?
Flush.
there.
What about this one?
Negative infinity.
That's
Okay, yeah, everybody see that? Now, all you gotta look at, once again,
Fudge.
to make this, we can make this process a little easier, we know that the leading terms are all that matter, right? This is all we need to consider.
I get it confused.
Everything else is gonna get dwarfed. So the leading terms, in the limit, the top is gonna give us, and we know that because the top has a bigger power than the bottom, it's gonna be infinity, right? So this part, if I can kind of color code this here, this part right here is telling us infinity. This part kind of, well, it's gonna be hard to circle all this, but knowing the sign of the top divided by the sign of the bottom gives us the overall sign. So if we have a negative number times positive 3, right, and that negative number is taken to an odd power, well, what is the sign of a negative number to an odd power? You what you really mean is negative, right? So we're gonna get negative divided by a positive number times a negative number squared would be positive. Does that make sense?
Negative.
So it's negative, yeah. Does that make sense?
Yeah.
Okay,
This actually makes sense.
good. So that's, we have a simple set of 3 rules, no big deal. Okay, now let's use this. I want to show you how we can incorporate this into the tables. And this also is very simple.
Yeah, right?
Okay, how about,
Skinny nose. What is it? This should be chapter 2.
I have so many cats.
I have like 3 narwhals and a narwhal. I have a narwhal.
okay, let's just try one like this.
I have a narwhal too, my turtle.
There's got a party cat.
She's a party in there.
Seriously, this cat is really, I've never seen it.
Nice.
Party cat.
My cat's like a party.
Okay, what about this guy? When I say sketch,
Oh no.
That's every lady.
okay, when I say sketch, that just means analyze using calculus, right? We're gonna get all that we wanna find peaks and valleys, points of inflection,
Oh.
all asymptotes.
Oh, no.
And that's really, so here's some other good news. We've done everything we're gonna do, essentially. We have to just kind of bring it together for the next test. Section 3.6 brings nothing new to the table. All it really did, well, just the tiniest of things maybe, but all it really does is it just synthesizes the stuff that we've been talking about with the tables into like the problem like this, where we're just gonna sketch a curve and we wanna find all the interesting parts of the function. Okay, and that's really all it is. So what about this? We gotta do a little calculus. So the calculus really is pretty limited here. The calculus is just, we wanna find relative extrema and points of inflection, okay? So we gotta take a derivative. How are we gonna differentiate that?
Quotient rule.
Quotient rule.
Quotient.
So what are we gonna get from quotient rule? Y prime equals,
X plus 1 times 2.
okay, so some people are thinking product rule, which is great, you can do that too. Let's go ahead and just use quotient rule. So that would be what?
X plus 1.
X plus 1, we gotta do bottom times
U
Two.
prime 2. Oh, see.
derivative of the top, right?
2x minus 1
Times
1.
1
All
divided by,
X plus 1 squared.
okay?
Shazam.
Shazam. Okay, so if we simplify that, let's try to do this all in one move here. So if I distribute the 2 and subtract, what am I gonna get on top? 3 on top, is that right?
Yeah. That's what I see.
Check me, 'cause I might not have done that right.
I
3 over x plus 1 quantity squared.
Yes.
Isn't that right? Because the
correct.
2 x's will cancel, and I'll get a 2 minus negative 1. Is that right?
That's correct.
So there's
Correct.
y prime. We're on a roll here. Let's get y double prime. Now, what would be the way to do this problem? Go on each quotient rule?
No.
No, I don't. How come?
No.
don't know.
I could, but it's a waste of time.
Yeah.
How come? Tony, why, talk to us. Why don't we want to use quotient rule?
Because it's a lot of work.
Because it's a lot of work, and the top is constant, right?
Yeah.
And so there's no need. All I would do instead is what?
Move it up.
Move it up.
Yeah.
Yeah, I would just, if I have a constant on the top and a power on the bottom, you just make it a negative power, and make negative exponent. So we'd rewrite this as, at least in our, I'm not gonna write it down, but at least in our head, it'd be 3x plus 1 to the negative 2.
Mm.
I better write that.
Yeah.
So,
Probably. Yeah.
so y prime, we could think of as being 3 times the quantity x plus 1 to the negative 2. So y double prime would equal what? It actually ends up being easier. Yep, times the derivative of what's inside, which is 1. Good. And so we end up, now we want to probably write it as a fraction, so we can analyze it more easily. Negative 6 over quantity x plus 1 cubed, yeah. So finding our critical numbers. All right, so now we got to kind of start to get a little more organized here. When we look at our original function, the first thing we want to do is we want to always ask ourselves, what's the domain of the original function? Are there any values that are excluded?
Yes.
Yes, there are in this case. What values of x are not defined for that function?
Negative 1.
Negative 1, because it makes the bottom 0. Everybody agree? Okay, so there's our domain right away tells us that x cannot equal negative 1, right? That's important because now when we analyze the derivatives for critical numbers, let's look for our first derivative critical numbers. Where do we look, again, for first derivative critical numbers? Where the derivative equals 0 or undefined. Okay, so here's our first derivative, right? Is that undefined anywhere?
Yeah.
Okay, it's undefined at negative 1. So is that a critical number? No is right. It seems like it ought to be. How come it's not? The function isn't even defined there, right? And so we need to add a little fine print to our search for critical numbers. Critical numbers really are only places where the function exists and the derivative is undefined or equal to 0, right? If the function doesn't even exist there, obviously you can't have a peak or a valley, right? Does that make sense? So there are no first derivative critical numbers. Oh, well, is it 0 anywhere?
No.
Where is a fraction equal to 0?
You're on top.
Where you get a 0 on the top, and the top is 3, it's constant, right? Are we good with this?
Yes.
Okay. What about the second derivative? Kind of the same deal, isn't it?
Mhm.
It's nowhere 0 because the top is constant.
Mhm.
And the only place where it would be undefined is where the function is undefined itself, right? Okay, now, that's not an accident. You can kind of think about this, it almost sounds like you're talking about a person or something when you get into this stuff at a certain level, but the derivatives just inherit all the discontinuities of the function, right? And so, and you'll always notice this. And this would happen, for example, what if the function had been defined everywhere, but the first derivative had been undefined at -1? Guaranteed, every subsequent derivative will inherit that discontinuity. It never goes away, which is kind of cool. I mean, it's amazing how math, it just works the way it should. So we get no critical numbers anywhere. Any possibility of an inflection point or a peak or a valley? No, none. So in a calculus sense, this is pretty boring. But there's some other stuff going on that's kind of interesting. So we know that we had a discontinuity at x equals -1. What kind of discontinuity and why? Going back to the beginning of the year.
Like a jump or an infinite.
Okay, it's going to be, so there's really, well, it could be lots of things. It could be a jump, it could be a hole, it could be an asymptote, but it turns out there's only one of those that it's going to be. How come? It's an asymptote, and why? What's the reason we know that we have an asymptote, a vertical asymptote at x equals -1? And here's our original function, and we can tell by looking at that. But what's the test? How do we know? What's happening at -1 that specifically tells us this is an asymptote?
Zeros on the bottom.
Say it again.
It's undefined.
It's undefined. Okay, it's undefined, meaning the bottom is 0.
Yeah.
And there's something else goes with that tells us it's an asymptote.
Approaching but never touching.
The top is not 0.
Oh.
Okay, that's the key.
Function is undefined as well.
There you go, and that's right. So it's where you have a 0 of the denominator and not the numerator, that's guaranteed to be a vertical asymptote, okay? So that shows up in our sketch. We can put it in our table. When we make our table then,
I don't have room for this table.
okay, when we write our domain down, we can do something like this. There's a number of ways we could do this. To me, the easiest way is just to write down 0, undefined, and I make a dash through the whole thing, and just write VA at the bottom for vertical asymptote.
Isn't it -1?
Oh, sorry, it is -1. You're right. When x is -1, y is undefined, there is no y value, and the dashed line is just telling us it's a vertical asymptote, and that's kind of nice because that's what a vertical asymptote looks like on our graph, doesn't it? It's vertical, it's a dashed vertical line. Okay, now, as we get more practice, this stuff is really kind of fun. I mean, you gotta cultivate your inner nerd a little bit with this stuff. It really is kind of fun. What you find is that when you get a vertical asymptote, it divides this table up into like separate universes. Each one is disconnected from the other one. And so that's going to show up. That's going to be important. I don't want to jump ahead too much, but just give you a little glimpse. We don't have time for a ton of examples today. What if I had, for example, just a what if, we don't, but what if I had at x equals 1, let's say we had a 0 of the first derivative, let's say, okay? Or even better than that, let's say we had a 0 of the second derivative, okay? Let's say we tested some points for whatever reason, and back here at -2, the sign of the second derivative was positive, and at +2, it was positive. Does that tell us if that's a point of inflection? This is really a pretty important point, a subtle point. It doesn't.
Yeah, because the last one said it was only that.
It doesn't, because that plus, or let's say it was minus here, sorry. That probably was a little confusing. Does that tell us it's a point of inflection?
No.
It's a change in sign, but this one doesn't count. It's on the other side of that
Separate
wall.
universe.
And so it's disconnected from the behavior of this side of the function. Does that make sense?
Yeah.
So I don't know what this is at this point, it's still indeterminate. I would have to know what's going on in here to know if that's an inflection point or not. That plus sign is irrelevant as far as that zero is concerned, because it's on the other side of the asymptote. Okay? So that's what I mean when I say they're like separate universes. I mean, they're totally disconnected, their behavior is, unless there's some symmetry going on, their behavior really is totally disconnected. I mean, if we had an even function or something and this were at zero, well then we know that it's gonna have folding symmetry even over the asymptote, okay? So, let's keep going with this.
Okay.
So we had a vertical asymptote there. Now, based on the new stuff that we have, what could you tell me about the limit of that function at plus or minus infinity? It's going to be a constant, and it's going to be 2. Okay, now what's that going to do? How do we show that on the table? Well, we can do this. Okay, remember how we said that our domain, if it's all real, it just kind of looks like that, and that just means, you know, it's going forever to the left and forever to the right, and there's no limitations other than the fact that we have, in this case, this one vertical asymptote. Okay, we could do something like this. We could say over here that the limit equals 2. Or maybe even a better way of doing that. I think, actually, that's a little hokey. I think I found another way I like it better.
Okay.
Do it this way. You can take your pick, but I think this is a little better. If you just say the limit is 2. And it's going to be that way on both sides, isn't it?
Yes.
Okay, is that an ordered pair? No, it's not. It's not an ordered pair. What does that actually mean about the behavior of this thing? Think about that for a second. We know from our rules that if we take the limit of a rational function with equally powerful polynomials top and bottom, we just look at the ratio of the leading coefficients, right? So we found that the limit of 2x minus 1 over x plus 1 as x approaches plus or minus infinity is 2. What does that imply about the function, though? What's that look like? If I go infinitely far out in either direction and the y value approaches 2, what's the function doing there? If I were to graph it, yeah, it's a horizontal asymptote, isn't it? Right?
I see.
Isn't that just a horizontal asymptote? Now, we don't know what's going on. Now, as far as that limit is concerned, the limit at infinity, it doesn't say anything about what's going on in here,
Oh,
right? In here, and we'll have to look, we don't know. In there is a big question mark, and we kind of know some things about that. There's a vertical asymptote, for example, but that's different, you know, it's different stuff. As far as the limit at infinity is concerned, all it says is that this thing is going to settle into a horizontal asymptote out there at the tails. Somehow it's going to have to connect that horizontal asymptote with whatever's happening in here close to home. But that tells us what's happening. It gets pretty boring way out to the sides. It just settles on 2 and it's a horizontal line, or it's nearly horizontal, right? Okay, so if we, and then we can do a couple more things. So we have horizontal asymptotes. This is what we perceive as a horizontal asymptote from our table, right? And we could even do that if we want to. Okay. Why not? We've got these derivatives taken. Let's find out what's going on there, though. There are no critical numbers, but any test point to either side of the asymptote is going to give us the overall behavior in terms of the first and second derivative. They never change, do they? if the first derivative changed over here to the right of the asymptote, we would have had to have had a critical number, right? Because doesn't a changing first derivative mean a peak or a valley? But they're guaranteed to be none because we had no critical numbers, right? We could pick any test point over here, any test point, pick a convenient one, and find the sign of the second derivative, and that also could never change because there were no critical numbers of the second derivative. So let's just pick one. Let's pick 2, how about? If we pick 2 as our test point, or actually, let's pick 0. Why wouldn't I pick 0 on that side? You're probably wondering. It's a good question. So if I pick,
Really?
okay, to be continued.
I thought they were.
Yeah, 2 more minutes.
I know.